Well, there she is. Good. Excellent. Well, hello, St. Mary's and Glory and Wamawini and Kabiro. And I think we had Asharika, but let me just have a look. Asharika, yes. Asharika don't seem to have a camera, which is a shame, but I think they were trying to sort that out. Anyway, hello, students. How very nice to see you. Today we are going to do a little bit more on solubility. And then, so we will look at what we did last time. Then we will look at the finish of solubility. Then last time, at the end of the lesson, some students waited and told us that they would like to follow some subjects, some topics. These included how to remember how to write chemical equations. So we will, if we have time, we will do some chemical equations. I think moles was very popular. People wanted to study moles. People wanted to study radioactivity and structure and bonding. What I would like you all to do now is just to think for a moment, talk to your neighbor, and just discuss, just for like literally 1 minute, are there other topics you would like me to try to complete before the end of the year, before the examinations? Because if there are, then it is better that I concentrate on those, not on what I think might be useful. So just 1 minute now, talk to your neighbor, your student neighbor, and tell me if there is another topic you would like to be able to cover. I'll just give you 1 minute now, literally 1 minute now. So just talk amongst yourselves. Tell me what topics you think you would like to cover. Another 30 seconds. I will ask each of the centers which I can see to tell me if there is anything, then I can just write it down and when we can see if we can cover it in the time that we have. So, St. Mary's, is there a topic which you think, oh, Glory, what have you got there? Sorry, I'll go with Glory first because they're showing me already. Across this way a bit. Closer, please. I can't see the writing at all at the moment. Ah, moles. Okay, so Glory would like to do moles. Okay, cool. St. Mary's, what are there topics you would like to cover, please? Periodic table, mixtures, hydrogen, carbon. Hydrogen, carbon, periodic table, and mixtures. Thank you. We will do what we can. That's St. Mary's. So, Kabiro, do you have a topic you would like to do? Or Wamoini? Oh, Dandora Girls. Hello. Hi. You don't look like a Dandora girl, but hey. So, Kabiro or Wamoini, do you have a topic? Usharika says moles and electrolysis. Okay. Energy changes. Okay. Thank you, Wamuini. Dandora Girls, is there a topic you would like to cover? Any other topic?
Oh. Chemistry. Electrochemistry.
Electrochemistry. Okay. I will try to produce some lessons where we look at. So far I have moles, radioactivity from last time, structure and bonding, the elements, hydrogen, carbon, their compounds, and the periodic table more generally, electrolysis, delta H, that's energy, Kabiro, carbon and its compounds, yes, carbon, its compounds, yes, and electrolysis, electrochemistry, okay, and chemical equations we will try to look at too. Thank you very much for that. Over the next few weeks, I will try to cover all of those topics. Today, though, I want to go back to what we did last time, remind you of what we did last time, go on just a little bit into solubility. I am not doing analysis using solubility to do analysis. That is the precipitation of iron and copper ions and so on. Unless you want to do that, I won't do it. But I will talk about natron and salt very briefly. And then we will look at balancing equations, not balancing equations. Can most people balance equations? Yeah. Just show me thumbs, please. Can you balance equations? Yes. Wamuini, yes. Samaris, balance equations, okay? Okay, good. Glory. Hello, Glory. Time to wake up. Can you balance equations? Oh, dear. Glory don't have any thumbs. That's a shame. Kabiro, can you balance equations? Kabiro? Okay, Dandora girls can. I know Dandora girls can. So we will look at something about balancing equations. But first then, something in the chat. Okay, get rid of that. So I'm going to go back to what we did last time. Where are we? Solubility. Okay. So last time we did solubility. We started with some definitions, and I said you have to test yourself on definitions. They were simple definitions. Then we did about calculating solubility. And calculating solubility is always in the mass of the solute, that is normally a solid, which we have dissolved in 100 grams of solvent, which is normally water. And we did a couple of examples where we were working out, okay, if we have the dish and the crystals, we work out the mass of the crystals, we have to work out the mass of the water, and then we have that work that up to grams per 100. Then we saw solubility curves, and we said they vary quite a lot, and there were some things you needed to know about solubility. Firstly, that some are much more soluble than others. Most solids become more soluble as it gets hotter. As I have said, the measurements are in grams of solute per 100 grams of water. Okay. And then we said above the line, if you had a mixture which was above the line, the mixture would be super saturated. On the line, it is saturated. Then we looked at finding the solubility of something. We said, hey, if we want to find the solubility at a particular temperature, we just draw up from that until it hits the line and then go across. So this is potassium nitrate, and at 50 degrees Celsius, up to the line, across 90 grams of potassium nitrate will dissolve in every 100 grams of water. But because as it cools down, less can be soluble, that means that as I cool it down, some will come out of solution. And we said in this example here, I pick this one. If I measure the amount which can dissolve at 90, and then I cool it down to 20, and I measure that amount, which looks like 34 here, then the difference between these two, from 90 down to 34, in other words, 56 grams cannot dissolve anymore, and so they will come out of solution. So we would see crystals, which we will see when we go to talk about natron and salt in a little while. Okay. Then we moved on. We said there were some which you need to know. So, for instance, calcium sulfate, not very soluble at all. And somebody, I can't remember who it was, somebody asked about why calcium sulfate is not very soluble. This is because when something dissolves in water, two processes have to happen. We have to put energy in to break up the solid, and then we get energy back when the ions, calcium, Ca2 plus, SO42 minus, go into water. If the energy back is not enough, it will not dissolve. If the energy that we have to put in to break the solid is too much, it will not dissolve. Calcium sulfate really doesn't dissolve. Some things, potassium nitrate, very soluble. Look, above about 50 degrees Celsius, more potassium nitrate is there than the water. So at 80 degrees, if I drew up to 80 degrees here and then across, it's about 160. That means 160 grams of potassium nitrate are dissolved in only 100 grams of water. Okay. Excuse me. So I'm going to stop sharing that one. That was what we did last time. I hope it was helpful. If you need to look at it again, your supervisors or teachers can access the YouTube video of the lesson which we did last week. And they have a copy of the presentation, that which I have just shown you. Now I'm going to share something else. So if I can find it. So this is a second one about solubility. This is solubility 2. In solubility 2, we're going to look at a very peculiar place. There are two lakes very close to each other, one just south of the border into Tanzania, which is called Lake Natron, and then there's Lake Magadi just in Kenya. Both of them are quite muddy. Both of them have quite a lot of dissolved salts. We get very strange effects. This is a dead flamingo, which has been covered with salt. It dries them out and it covers them and makes them, they feel like they are made of rock afterwards. Now, this is the geography. This is where it is. This is the Magadi soda company. It's the biggest soda company in Africa. And it is at this wonderful lake, and it is a beautiful lake. But along the shore, you can see the solid is crystallizing because there's not enough water. What they do is they use some automated, they're like diggers, like they dig it up, and they collect the natron. Now, natron is a strange substance. It is not just one chemical. This is the graph of the solubility of natron with temperature. There is a reason for it dropping afterwards. So the solubility starts quite low and rises with temperature very quickly until we get to about 35 degrees Celsius, and then it drops. Now, natron is a very odd chemical. This is the factory, and whenever you see a factory with chimneys and with boilers like this, this is for heating, and this is what they do. Now, I'm going to just show you this slide properly. So the the chemical is called, guys, can you mute, please? Can we mute, please? Thank you. So, what is Trona? You have to know the formula of Trona. Trona is what we call a double salt. Now, a double salt is something in which you have two separate chemicals, and they are basically joined in a whole number ratio. So this is sodium hydrogen carbonate and sodium carbonate, and it's 1:1. Now, what we do is we combine their formulas, as I will show you in a moment. Here, if we look at this, we have two sodiums in sodium carbonate and one sodium in sodium hydrogen carbonate. So it's Na3 and 1H and 2 CO3. So this is Trona. You don't have to worry about the 2H2O. Okay, you will not lose marks if you don't remember the 2H2O, but you do have to remember Na3H CO3 twice. Okay, CO3 too. Okay, now when the water evaporates from the lake, this comes out of solution. It also comes out of solution at night because it cools down, because the lake cools down. So they collect it in the daytime when it has been precipitated. And it is concentrated and then dried and then heated. So you need to know Na3HCO3 twice, and it is it comes out of solution and then it is heated. Now, when it is heated, carbon dioxide is driven off it, is lost, carbon 4 oxide. So this is what happens. Here is the equation. This is the other way of writing it. This is with it separated into the two salts, sodium carbonate, sodium hydrogen carbonate. I'm sorry, I've got capital A here. That's wrong. I think it must have been when I was typing it in. I must have had caps lock on, but it turns into sodium carbonate, which is called washing soda, and carbon dioxide and water. So you can either write this here in yellow here or this yellow here. Okay, either one of them is correct. So I would write this one, Na3H CO3 twice, goes to 3 Na2CO3 and CO2 and 5H2O, but you'll need 2 at the beginning. Okay, so natron double salt heated forms Na2CO3. Na2CO3 is called washing soda. It's called washing soda. It is used in many, many different chemicals. It is used mainly in washing things, like in washing powder, but it is also used in making glass and quite a lot of other things. All right, so that's natron, sorry, that's Trona, which comes from Lake Magadi, double salt, NaHCO3 and Na2CO3. That's the overall formula, and it breaks down when it is heated to make Na2CO3 and CO2 and H2O. Okay. And salt is the other industrial produced chemical that they want you to know about. And that is on the way north from Malindi if you're going up towards Lamu. Ngomeni is a big center for doing it. It is a set of lagoons. Now, salt is not very soluble compared with many other sodium compounds. So sodium nitrate, much more soluble. Nitrates are all soluble. But sodium chloride doesn't change its solubility very much. It is quite soluble when it is cold and about the same when it is hot. So what they do is they pile it up. They use people and machines to pile it up. the water drains out of it, the sun heats it, and in heating it, it evaporates the water, and then it is dried completely, collected in very, very large pits, and then it can be used as salt itself, but more often it goes into electrolysis. Now, we will do electrolysis in another lesson, so it is not necessary to write this down, but this is the electrolysis of molten sodium chloride. If you electrolyze molten sodium chloride, you produce two chemicals. And I'm just going to go through this very quickly now here. I hope you will see it. So I start with NaCl, and it turns into Na and Cl2. Obviously, to balance it, I would need two of these, and I would get two of those. But what is happening is that the sodium turns into sodium ions, well, it's present as Na ions, and the chloride is Cl minus ions. Now, to get rid of a positive charge, we add electrons. So what you will find is down here, this is the cathode here, and it is negative, and the electrons are added, and the sodium ions become sodium atoms. Now, because sodium is quite not very dense, it goes up these pipes and out. Chloride, we don't say chlorine, we say chloride. It loses the electron and turns into chlorine. But chlorine goes around in pairs as Cl2. So the equation is 2Cl minus 2 electrons turns into chlorine. And the chlorine here is going up and being collected. Now, chlorine is used for many things. Sodium is used for many things, but we will go through this when we do electrolysis. All I want you to know is, going back a little bit, is that sodium is not very soluble at any, well, it's the same solubility at all temperatures. It is piled up, dried out, and then electrolyzed. Okay, and the electrolysis produces sodium and chlorine, both of which are very important chemicals. So this is the overall pattern of what happens to these two chemicals, sodium chloride and trona. Trona can also dissolve in the sea, but it should say in water. So the first thing they do is they dry out, they get the crystals out by what we call fractional crystallization, by making the solution too concentrated so that the crystals come out. Now, the crystals of trona and the crystals of sodium chloride are dredged or scooped or dug out and then crushed up. Now, that is all that happens to the sodium chloride before electrolysis and so on. But the trona is then heated in a furnace, which, as we saw, produces carbon oxide, carbon dioxide, carbon 4 oxide, and soda ash, which is sodium carbonate, is sodium carbonate, which is what we call washing soda. So in other words, they go through the same process until we get to crushing. The salt is not heated up, but the trona is. Okay. There is a useful table for solubility, which you will get because I will send your teachers the PowerPoint, the presentation. But this is a useful way of remembering solubility, because quite often they ask you a question about solubility. And the simple way is to divide it into three groups. Firstly, group 1 and ammonium salts all dissolve and all nitrates dissolve. So it doesn't matter whether it is calcium or tin or gold nitrate, it will dissolve in water. And it doesn't matter whether it is sodium chloride or sodium sulfate or sodium carbonate, they will all dissolve. Then the ones which really do not dissolve are the carbonates and the hydroxides. So the carbonates and hydroxides, if you are asked calcium carbonate, will it be soluble? If you're not sure, you would guess and say no, because we have just said that sodium and potassium and ammonium salts are all soluble. So sodium, potassium, and ammonium carbonate will be soluble, but none of the others. Copper carbonate, not soluble. Calcium carbonate, not soluble. Lead, not soluble. Hydroxides, very, very similar. Most hydroxides are not soluble. Copper hydroxide, lead hydroxide, all these, they are not soluble. In the middle are some which are soluble, which are the halides, that's chloride and bromide and iodide. They are mostly soluble, but not lead and silver. And the sulfates, which are mostly soluble, except for these three, lead, barium, and calcium. I'm going to move on because I don't want to take too long looking at that. But if you have scribbled down some bits, some little bits of it, or you look at this later, you could screenshot, you could take a picture of that solubility table, and it is worth trying to learn. The last bit is about hard water, and I'm very, very briefly going to talk about hard water. I expect your teachers have done it well, but if you later want to do some organic chemistry, it is important in terms of soap and in terms of detergents. Okay, so here is hard and soft water. Soft water is mainly just water. It may contain sodium, it might contain potassium, but it mainly comes from rain and in this country, snow, or on the top of Mount Kenya sometimes. It is also produced by reverse osmosis, which happens down in a couple of places on the coast, and distilling water as well. There is also something called deionized water, but they are all soft water. What they mean by soft water is it does not have magnesium or calcium ions, because hard water has calcium and or magnesium ions. Now, quite a lot of well water is hard water. Mineral water is always hard water. And water with high pH, that means a pH greater than 7. So you quite often hear that it is very good to drink water with a pH of 8. Well, yeah, it's good to drink water. pH of 8 may be better, but only a bit. So hard water contains calcium ions, magnesium ions, one or the other, or both. Where I live, it is very hard water. And I know that because if I try to make bubbles with soap, it takes a long time. My brother, who lives in London, lives in soft water area. When I go to his house, the soap makes bubbles straight away. And that is how you tell. Okay. Any questions so far? Any questions so far? Does anybody puzzled, confused at all by that so far? No? Okay, that's good. If you have a question, put it in the chat or hold up a piece of paper or just unmute yourself and talk to me. Tell me. I'm going to now go on to writing equations, and I'm going to concentrate on acids and alkalis. And there is a chance for you to do some examples. So it is worth having a piece of paper and a pen or pencil and seeing if you can do some of these equations. Okay, so here we go. I'm going to share my screen again. Somewhere. Right. This is called writing equations for reactions involving acids and bases, etc. In other words, it's one which is not just about acids and bases. I want you to remember that acids and bases have a specific definition, that an acid produces hydrogen ions and bases produce hydroxide ions. That is, acids produce H plus and bases produce OH minus. They must be AQ. In other words, they must be dissolved in water. So that's a definition that you need to know. Acids, hydrogen ions, bases, hydroxide ions. Now that means that they split up, the acid will split up to produce H plus ions, or the base to produce OH minus ions. But there is a very important symbol, which I'm sure you know, which is the reversible arrow. Now, the reversible arrow is important. What it means is that the chemicals on the left are turning into the chemicals on the right, and at what we call equilibrium, the ones on the right are turning back into the ones on the left at the same speed, the same rate. So although we might have 100 of these and 100 of these, they are swapping back and forth. One of these turns into these, one of the hydrogen ions and the chloride ions turns back into the unsplit, the undissociated HCl. Now, what I'd like you to try and do is just to try to write equations. Just take a couple of them. So, for instance, if I said, OK, I'm going to do the HCl one, I know we have just seen it. I would simply write HCl, then the reversible arrow, H plus, I should write AQ, and Cl minus AQ. If it's a base, and down here they are all bases, it would split to give the OH minus, because that's what all bases do, and the other part of it, whatever that is. Okay, so what I'd like you to do now is just have a little bit of a go at writing those equations, see if you can split them all up. There's a cross here. This is because this is ethanoic or acetic acid. Those hydrogens there, the CH3 bit, those hydrogens there do not ever split up. Okay, they never come off as H plus. Only that one will. Only the one on the right. Okay, so just have a few moments. Just see if you can write a few of these equations. I will give you all the answers in just a minute. So just see how you get on. It's just good practice. You don't have to write it down. You could just think it, but it's useful to practice writing. Oh, St. Mary's can't write. Oh, dear. Very good, Kabiro. Well done. Very, very good. Well done. Just keep going. If you want to show me a couple of examples, put your name on the paper, then you will be famous. I will be able to say, hey, well done, Mary, or well done, Joshua, or whoever. Does that say Alicia? I'm sorry. Can you just go down just a little bit, please? That's better. Not quite. If you look at the number of hydrogen ions, there's one hydrogen missing, so you'd have to be careful that they are exactly right. Okay, exactly right. A little bit closer, please, Kabiro. Student at Kabiro. Excellent. Well done. Very good. Very, very good. What's your name? I can't read it. I'm sorry. That's very, very good. Well done, St. Mary's. Oh, a little bit closer. What's wrong with my screen? Cedric. Cedric. Well done. That's excellent. Well done. Very good, St. Mary's. Excellent. Excellent. I'll go through all of it in just a minute. Do try some of the bases as well. Do try some of the bases, please. Oh, yeah. Kaviro, just think about if the H has gone to H plus, what has happened to the OH minus? That's really good, Kaviro. Well done, Cindy. Cindy from Kaviro is in first place for having got down to water. Oh, Dandora, come on, show me. Don't be shy. Come on, you're right next to it. You're allowed to show me. Very good. Excellent answers. Excellent answers. Wamuini. Very good. You guys are really good. You guys are very, very good. Okay. We just have one more minute doing this, and then I will share the answers with everybody so we can see. We've got some great answers from people. Well done. For all glory. Glory. Some of them can't work. I know it's a long day, isn't it? Right, here we go. Here are the answers. Ready? So I'm going to do the answers. Now, in sulfuric acid, it can split up in two different ways. It can either split up to form one H plus and HSO4 minus, or it can split to make two H plus and SO4 2 minus, and both are right. Okay, both are correct. So H2SO4, because it has two hydrogens, can lose just one or can lose two. Both are correct. Generally it would lose one and then a second one. HNO3 only has one, so it will go H plus and NO3 minus. CH3COOH, ethanoic acid and alkanoic acid. This hydrogen comes off, so it's H plus and CH3COO minus. Never forget the minus on things. Now, water is odd. Water can split to give the H plus as though it is an acid and the OH minus as though it is a base. Actually, only 1 in every 10 million molecules splits up, which is why water does not behave as an acid or an alkali. Can we mute, please? Can we mute, please? We have could somebody mute, please?
Kuna subject ine na si mchezo. Angalia hapo.
Thank you. Okay, I've done the sodium hydroxide. The ammonium hydroxide will give, it doesn't matter which order you write it in, NH4 plus and OH minus. And calcium hydroxide, just like sulfuric acid, it can split to give one or both, but it's normally splits to give both OH minuses like that. So there is our set of equations. I hope you got them right. Very quickly, what's the difference between a strong and a weak acid? In a strong acid, it is more like a one-way arrow. So if you look down here at the equation down at the bottom, this is like a one-way arrow. In a weak acid is like this, and most of them are like this. So in a strong acid, there is about 1% of that, and 99% is split up. And in a weak acid, it's about 99% not split up and only about 1% split up. So that's how acids can be weak or strong. Some of them give many hydrogen ions. Some of them stay mostly together. Okay, I'm sure you knew that. So this is about writing equations. So we're going to just go to writing equations. Here are 3 general reactions it is worth you knowing. If you do not know these, I would write them down. These are how salts are produced. So a salt is produced in one of 3 ways: either an acid and a metal, an acid and a metal oxide or hydroxide, and an acid and a metal carbonate. Now, this is very important because if you know this, it will help you write many equations. I will show you how. So acid plus metal oxide or hydroxide, and acid plus metal carbonate. Now, the acid plus metal only works if it is a reactive metal. So copper, gold, silver do not react with acids. The metal oxide or hydroxide is called a base, and sometimes they will talk to you about a base, but a metal oxide or hydroxide is called a base. And although I say carbonate here, it could be carbonate or hydrogen carbonate. They work the same. What is rather important about this is that it allows us to write equations, okay? So I want you to try to remember this. So an acid and a metal makes a salt. An acid and a metal oxide makes a salt. And an acid plus a metal carbonate makes a salt. But with a metal, it's just hydrogen. With the metal oxide or hydroxide, it's water. And with the carbonate, we get water and carbon dioxide. There they are. Those are really important things to know. Acid and metal make salt and hydrogen, and so on. This is because if I have an acid, don't write this down, I'm just going because you're going to have examples. But if I have a, oh, hello, what's happening here? Hang on. If I have an acid plus a metal, then I have, oh, heck, sorry. Just a moment. If I have an acid and a metal, then I might have, oh, why is this happening? Come on. Sorry, there's something wrong with my pen at the moment. Ah, what is happening? So if I have HCl and a metal, then the metal and the hydrogen swap. And so the only thing that is left is hydrogen. If I have an acid and a metal oxide, then the hydrogen and the metal swap. So the metal chloride is formed in this case, and I have water. If I have an acid and a metal carbonate, then the hydrogen and the metal swap. And then I have the hydrogen with the carbonate here, and that makes water and carbon dioxide. We'll see equations in just a minute. Okay, so with just the metal, we get just hydrogen. With the metal oxide or hydroxide, we get water. With the carbonate, we get water and carbon dioxide. Okay, I'll just get rid of all of that. Okay. Whoa, hang on. Where did that come from? Something happening on my screen, which is not on yours. All right, okay. So here we are. So let's have a look at these and see if we can start to predict. So here's an example of one with a reactive metal, zinc and hydrochloric acid. The zinc and the hydrogen swap, so the zinc goes with the chlorine, zinc chloride, and hydrogen. With a metal oxide or hydroxide, this is copper oxide, sulfuric. The metal and the hydrogen swap, exchange places, so I get copper sulfate and H2O. With the metal carbonate, the metal and the hydrogen swap, so I get calcium chloride here. And then there's enough here in the two hydrogens and the CO3 to make water and carbon dioxide. Okay, I'm going to show you those. I'm going to show you some examples of those. But first, you need to know which salt is produced. And the most important three are this one, and this one. These are less likely. And the important thing to know is that every time you have hydrochloric acid, you will make a chloride. Every time you have a nitric acid, you will make a nitrate. Every time you have sulfuric acid, you will have a sulfate. Now, if we go back, and you know this, and you know the acid plus the metal makes salt and hydrogen, and acid plus metal oxide makes salt and water, and acid plus metal carbonate makes salt, water, and carbon dioxide. And you know that hydrochloric makes a chloride, nitric makes nitrate, sulfuric makes sulfate. Then you can write equations for any of these. Let me give you an example. So let's predict what will be formed in these. These are just these written out. So let us see if we can predict what will be formed. Okay, so this first one is acid plus metal. If we can remember the first equation, that means acid plus metal, that means it will be a salt and just hydrogen. Which salt? Sulfuric acid makes sulfate. So it must be magnesium sulfate and hydrogen. And it is. Okay? Get the idea? Acid plus metal always makes salt and hydrogen. Which salt? Well, we have magnesium, and it is sulfuric acid, so it must be magnesium sulfate. Next one, nitric acid, copper oxide. That is the second equation. Oxide makes water. So I'm going to get a salt and water. And we are starting with nitric acid. So we will get copper nitrate and water. Do you see? It is just general equations. Next one, hydrochloric acid, calcium carbonate. Carbonate. Carbonate makes a salt and water and carbon dioxide. Which salt? It is hydrochloric, so it must be chloride, so it will be calcium chloride and water and carbon dioxide. What do you think the next one will be? What do you think the next one will be? Can anybody tell me? Sulfuric acid and sodium hydroxide. Wow. Dandura girls. Have a look. Just see if you can predict the bottom two ones. See if you can predict the bottom two there. So sulfuric acid and sodium hydroxide. Who is that, please, at Dandura? Put your name on the piece of paper. Sulfuric acid and sodium hydroxide. Well, the second type of equation was sodium. Let me just make you bigger. Sorry, I'm trying to see too many at the same time. Mathari mix. Let me see yours first. Hang on. Let me just make your pictures bigger. Let me make pictures bigger. Hang on. Just going to make them bigger. Oh, come on. Sulfuric, sodium sulfate and hydrogen water. It's Phyllis, you have to be careful because it's not going to have all of those chemicals in. So we have to be very precise. Sulfuric acid and sodium hydroxide. I'm not asking for formulas at the moment. I'm just asking for their names. We only have 10 minutes, so let's see if we can get them right. So this is sodium hydroxide is like oxide. So that will give us salt and water. Okay, a salt and water. St. Mary's. Let me just pin you. Oh, come on. Hang on. Wow. Well done. Very, very good. Well done, St. Mary's. Be proud. And Kabiro, sodium sulfate, can you take it a little bit further away? Sorry, let me just pin you and make it easier for me to see. Hang on. Oh, you've disappeared. Oh, there we are. A little bit further away, please. Kabiro. Oh, I think your camera is jammed. Ah, sodium sulfate and water. Very good. And I can't read your bottom one. Can you move just a little bit further away? I'm sorry, your camera is not recording yours properly. I'm sorry. Oh, hang on. That might be better. Potassium. I think you've got it right, though it's not easy for me to see your screen, which is a shame. But anyway, so here we are. These are the answers. The number 4 will be sodium sulfate and water. The third one will be potassium nitrate and water and carbon dioxide. Now, so that is how we write the word equation. When you have got the word equation, it's easy to start to write equations like this. So HNO3, you've got to remember that copper has a valency of 2, so it would be CuNO3 twice, CuNO3 2, and H2O. I'm not balancing them at the moment. CaCl2 and water and carbon dioxide, these are not balanced necessarily. Na2SO4 and H2O, and KNO3 and H2O and CO2. For those of you who are not sure how to work out the formula of something, let me just show you sodium here. If I look at sodium, sodium is in group 1 and so has a valency of 1. Sulfate normally joins with 2 hydrogens. That means that sulfate has a valency of 2. If I swap those numbers over, I get Na2SO4. So that's how I find that it's Na2SO4. Most of you will be able to do that, but that's how you write it. Okay, now there are other types of reaction. And I'm going to look at 4 very quickly because we only have about 5 minutes. I'm going to look at decomposition. I'm going to look at combustion. I'm going to look at double decomposition and direct combination. So here we go. Whoops. So decomposition. If in a question you can see that 2 chemicals are produced from 1 chemical, that is decomposition. It is breaking down. So you're looking for 1 chemical turning into 2. In that case, only the elements in the original compound will be there at the end. So calcium carbonate is heated. There are many questions which has calcium carbonate being heated or something else being heated. If you look at calcium carbonate, only 1 calcium, only 1 carbon, only 3 oxygens. What can I make? Well, the easiest thing I can make is CaO and CO2. So that will be the equation. So in decomposition, 1 chemical becomes 2 or 3. In the equation, when we were looking at Troner, it showed heating it, producing 2 chemicals. That's it decomposing. All right, combustion. When something burns, oxygen is added to it, and all of the elements in the thing which is being burned are separated and turned into their oxides. So this is ethanol. This is alcohol, alkanol, the second alkanol. When ethanol burns, what will be formed? Well, ethanol is made of carbon and hydrogen and oxygen, so it will burn just to make carbon dioxide and water. There's the equation. It's not balanced. It's not balanced. Can anybody balance that for me? Look, all I have done is I've said it has carbon and hydrogen in it, and they form their oxides, carbon dioxide and water. And to balance it, well, for those of you who are looking carefully, here we have 2 carbons. So I will need 2 carbons over here. So it will be 2 CO2. And here I have 5 and 1. That's 6 hydrogens. So I will need 6 over here. That means 3 waters. Now out of this, I have 4 oxygens there and another 3 here. That's 7, but there's 1 here. So I need 6. So it's that. Okay. If you're not sure about doing that sort of thing, we can look at it another time. Next type of equation is what we call double decomposition. There are only these 5 that you often come across. The acid ones, these guys, decomposition and combustion, and then double decomposition and direct combination. Double decomposition is where salts swap. Okay? So when we add sodium carbonate to silver nitrate, the nitrate and the carbonate swap. There we are. Na2CO3 becomes NaNO3. AgNO3 becomes Ag2CO3. Why Ag2? Well, because silver and sodium both have a valency of 1, a combinational power of 1. Direct combination is just the elements joining together. You just have to be very careful that you get the formulas right. The formulas are not easy sometimes. So iron burns in chlorine, and you need to know that iron, when it burns in chlorine, forms iron 3 chloride, not iron 2 chloride. There it is. I haven't bothered balancing any of these, so when you receive this, if you look at it, you can have a go at balancing them. They're not terribly difficult. So that's it. 1, decomposition. 2, combustion. 3, double decomposition. 4, direct combination. And before all of those, we had the acid and metal oxide or hydroxide, and acid plus carbonate. If you can remember those, and you get good at balancing equations, by thinking for a minute, you can work out what is formed in it. Okay. It's been a long day for you guys. You've been at school all day. You're very patient for coming to chemistry and staying till the end. I'm going to stop recording now.